Good day! This video is a second part of our online material for Physics 10 Module 2. How did we, human beings, come to realize that the Earth is not the center of the universe? This is Dr. Janro Bantang from the National Institute of Physics, UP Diliman. A PDF version of the notes should be available for download via the URL shared in the description below. In the previous material, we discussed the early models of the universe and correlated them to the philosophical position of the early Greeks. We ended with the most accurate and philosophically consistent model of the universe, a geocentric model. This model, the Ptolemaic system, persisted for more than 1,400 years. In this section, we shall discuss the alternative models of the universe that arise due to many considerations, including simplicity and accuracy. Here are the main references for this part of the module. I think it is worthwhile to read the Galileo Affair series of 9 short articles by a science writer, Michael Flynn, since it contains direct materials to actual letters and writings of the personalities related to the historical events surrounding the infamous Galileo Affair. The other materials also help you understand why the early Greek philosophers chose the geocentric model as the most plausible model to explain the awesome display in the heavens. In our previous material, our discussion dealt with the ideas and datasets that allowed the early Greek philosophers and astronomers to generate the geocentric model, culminating with the Ptolemaic system. The important historical figures are shown in this timeline. It ends highlighting Ptolemy in the 1st century AD. Other philosophers and astronomers are not included in this timeline. As a review, notice the 3 main steps of development of the geocentric model, from the simplest model of Plato to the mechanical model of Aristotle and the purely mathematical but highly accurate mathematical model summarized by Ptolemy. Plato's model is based on his idea that the outer appearance of the heavens, the diurnal or daily motion of the heavens, as well as its annual motion, must be explained by some inner mechanism, just as he explained in the allegory of the cave. He also conjectured, based on the seeming harmony between the assumed basic elements of the universe and the geometric shapes to the known but yet inaccurate distances of the moon, the sun, the planets, and the background stars. The mechanical model of the universe can be said to have started with Aristotle. Based on the elaborate philosophy of reality, known as physics and metaphysics, he had to include additional features to the developing model of Plato. Aristotle successfully generated a model that requires only one ultimate source of motion. This ultimate source of motion, he called the prime mover, essentially caused a series of cause-effect relation, like gears and cogs in a machine, throughout the system of crystalline spheres carrying all the heavenly bodies along. This sort of clockwork motion is said to generate the appearance of the diurnal and annual motion of the heavens. The discovery of more intricate details of motion, especially that of the retrograde motion of many planets, because of the advances in the astronomical technique of observations, resulted to a need for a more complicated model. This resulted to the relaxation of the physics, the mechanical cause-effect relation, and the utility of a more mathematical explanation behind the appearance of heavenly motions, thus just for calculations. The Ptolemaic system summarizes the development of many mathematical devices over a few hundred of years. It focuses on creating the appearance without regard to those that cause them. We now move towards the early scientists that reaped the less popular but very critical scientific developments that happened during the Middle Ages, often referred to as the Dark Ages. The early scientists we refer to are those in the age called Enlightenment, popularly contrasted to the Dark Ages that precedes it. Our discussion focuses, but to mention background development during the Middle Ages, on the works of Copernicus, Brahe, Kepler, and Galileo, culminating with some related works of Newton. For temporal perspective, note that the Philippine archipelago, represented by some islands in the Visayan region, is more famously known to have been discovered by the Europeans through the historical arrival of Magellan in 1521. Meanwhile, Christopher Columbus reached the Americas just a year short of 30 before 1521. Incidentally, we will be commemorating the 500th year of this event in 2021. That's next year as of this recording. For the remaining part of this material, we shall take on two major items. First, we will discuss the philosophy developed in Europe by the end of the medieval era. And second, we will move taking on the development of alternative models of the universe driven by such philosophy and the ever-increasing complication of the Ptolemaic system just to keep up with the new and more accurate astronomical data sets. The medieval period is a period in the European history, beginning with the fall of the Western Roman Empire about the 5th century and ends with the beginning of the modern period by the late of 15th century. The medieval period is middle in a sense of being mid-section in the traditional division of world history, the period between classical antiquity and the modern period. Progress in all areas in the medieval period has been disrupted in many fronts: war, famine, internal leadership strife, and many others, not to mention personal flaws in character of political and religious heads. Note that the most significant of these is the attack of the neighboring cultures into Christian Europe, resulting to the increased efforts of the kings and princes to send soldiers and volunteers to fight against the incoming onslaught. Perhaps this is the reason why these periods of European history is metaphorically dark. Pressures from both within and without the many kingdoms of Europe makes it an interesting topic beyond Physics 10. If you are interested, you may read further into related topics such as the rise of Islam, interaction of Arabic philosophy with European counterparts, and many others. It is just as important to note that all these factors greatly affects intellectual progress and therefore scientific progress as well. But overall, this is not a purely sad note, as we shall see in the following slides. During the so-called High Medieval Ages, roughly between the beginning of the 11th century until the middle of the 13th century, an unprecedented human flourishing happened in Europe. Many socio-cultural factors come together in Europe that brought about great intellectual development, from theology and philosophy to economic growth and great innovations. By the late 12th century, the schools operated by the Catholic churches, established for training people for priesthood, has spread throughout Europe and replaced the original monastic or isolated schools. These cathedral schools soon opened to many others. By the end of the 13th century, many has become universities that we know today in the old cities of Europe. Shown on the right is a typical portrait of a medieval doctoral lecture. This scenery is a standard picture of a modern classroom. The common format of lectures and seminars or reading of work during conferences originated from the traditions of these times. One of particular interest is the existence of an academic mace that may be traceable from the personal weapon of the king carried by his bodyguard. By 14th century, such mace has become ornamental, carried by sergeant-at-arms, as we see here in the same picture. The teacher's seat, in modern times with teacher's table, is the very noticeable seat of teaching authority in the times of old. Just like in Senate and in the House of Representatives, such mace is usually in display when any of these houses are officially in session. The mace is removed when out of session. According to a Wikipedia entry, the mace symbolizes the legislative authority of the House of Representatives. As stipulated in Section 165 of the House Rules, it is displayed at the foot of the Speaker's rostrum whenever the House is in session and is used by the Sergeant-at-Arms to enforce order in the House upon the Speaker's instructions. In UP, we have ornamental and ceremonial mace for the office of the President and also for the office of the Chancellor. At least for Diliman, I personally saw one in one of my visits to the Chancellor's office a long time ago. Such mace is a symbol of the authority of the university president and is carried by the secretary of the university during academic processions. You may also notice the classic toga robe or gown worn by those who graduate together with a ubiquitous toga headgear or hat, usually decorated with personal effects if you are in Germany or elsewhere in Europe. The graduation gowns must have originated from the priestly vestments, since graduation with cathedral schools usually mean you are also ordained as a priest. The colors added to the robe has special meanings. Colorful additional ornaments usually mean special or high distinction, indeed very distinguishable from all black or dark motif of the gowns. Thus is the origin of the phrase to graduate with flying colors. During our time, the colored robe usually means conferment of a post-baccalaureate degree. In UP, we have replaced the gown with sablay. Sablay is an indigenous loose garment, simple yet elegant, and is used traditionally for formal occasions. Sablay began to replace the traditional toga gown and hat starting 1990s, and officially instituted as replacement since 20 years ago in 2000, the year I got my BS Applied Physics degree. It is rumored to have been adopted from the costume of babaylan, Philippine shamans, indicating a consistent undertone of religious origin. Meanwhile, it is a great and practical relief from inappropriately unventilated graduation costume in a tropical region where university graduations are traditionally held during high summer time. These interesting interactions of historical events and cultural developments provided the right mixture of ingredients towards the great intellectual progress that led to fast scientific progress. Science always depends on their philosophical foundations. An illustrated book of the high medieval period called Hortus Deliciarium or Deliciarium, a work by an abbess, a nun, provides us a graphical and a very poetic way of showing how philosophy, the queen, sits at the center of all the arts, from grammar to music, to mathematics, to astronomy, providing these, as it were, streams of wisdom, called the seven liberal arts, the knowledge that leads to liberty or freedom. Liber rather than liver, means to be free. The liberal arts, composed of trivium and quadrivium, forms the basis of our basic education, elementary and high school, or the K-12 program. Main subjects revolve around language, Filipino or English, mathematics, and science. The general education program in UP follows essentially the same principles. There is no denying that the sciences in the medieval times are generally founded on the philosophy resting on the Aristotelian tradition. By this time, philosophy have moved from purely Platonic to the Aristotelian in doctrine. These Aristotelian traditions have been questioned and doubted by the medieval philosophers, especially since the main focus is the development of theoretical arguments and scriptural exegesis. In fact, the need to develop philosophy of reality is rooted in the Christian inspiration to use reason as a way to further understand the faith that they have received. Anselm of Canterbury, for example, by the end of 11th century has written Credo ut intelligam, the Latin for I believe so that I may understand. For these people in the high period of the Middle Ages, faith and reason complement each other. They fiercely defended this doctrine against fideism, the belief in pure faith without human reasoning, and against averroism, or the belief that faith and reason belong to two different areas without intermingling or interface across each other. The scholastics are the ones who try their best to provide arguments how reason supports their Christian faith. During the period before the modern era, we can summarize that many philosophical conclusions are supported, others are opposed. Philosophical positions are often pitted against each other within the developing universities where academic freedom is granted by the church and civic authorities. This condition provided the appearance of the best foundation on which the new sciences are to appear for reaping of the modern times. With these historical and cultural backgrounds, it was in the medieval period that the physics according to Aristotelian tradition is tested and developed. This development culminated with the time or in the time of Copernicus, Galileo, and Kepler. This thesis, called continuity thesis, well, you can Google that, stating that there was actually a continuous progress of scientific thought from the medieval era into the scientific revolution during Renaissance. The continuity thesis is started by Pierre Duhem of France during his study of the history of science, especially working on the scientific notebooks of Leonardo da Vinci. Duhem even claims to the point that the Christian culture is actually responsible for synthesizing and supporting scientific thought because it encourages the faithful to discover the art of the divine in created things. The translation of the Greek and Arabic scientific texts in the 12th and 13th centuries did a great impact in the scientific development during the High Medieval period. These are just two of the four factors shown here. These he proposed in his book, The Foundations of the Modern Science in the Middle Ages, whose first version is published in 1996, a year after I entered UP Diliman as an applied physics student. You can also read on the cosmological theories of the medieval age and how they argued, discussed, and measured things related to topics such as infinity, space or place, time, void, and even plurality of worlds. If you search for medieval European scientists, you will find a lot of them who studied astronomy, physics, biology, botany, mathematics, philosophy, psychology, and ethics, among other things. There is even a German mathematician and astronomer who seemed to accept the findings of Aristarchus, the Greek we mentioned, to have proposed a heliocentric model of the universe. It is overwhelming to see on how these scientists have initially explored and did all the mistakes in their scientific adventure and discovery. We now proceed to the discussion of the cosmological ideas by the time of Copernicus, Brahe, Kepler, and Galileo. In the Middle Ages, we can safely say that the Ptolemaic model is widely used and developed by adding more devices or adjusting them according to the increasingly accurate astronomical data. The increasingly becoming accurate astronomical data is brought about by the utility of new technological tools such as the quadrant and the sextant. The sextant and the quadrant provided Tycho Brahe or Tycho Brahe the opportunity to record vast amount of data on the positions of the planets and the stars over a long period of time. The use of telescope in viewing the celestial objects such as the moon and the planets later in the beginning of the 1600s became widespread. It is said that Galileo greatly improved the telescope from the Dutch prototypes used for military applications. This improvement of Galileo's telescopes from 3 times to 8 times magnification allowed him to draw amazing sketches of the surface of the moon. Meanwhile, retrograde motion remains one of the major anomalies from the regular motion of the planets as well as of the Sun. At this, no model rivals well with the highly adjustable Ptolemaic system in terms of accuracy. The main downside of the Ptolemaic system is really its burgeoning complex addition of epicycles upon epicycles as well as the arbitrary shifting of cycle centers. A YouTube link explaining the retrograde motion is shown here. The complications of the Ptolemaic system led Copernicus to consider simplicity as the greater measure of nearness to the truth about reality. The same complications led to philosophers to suspect that the system lacked reason or support of natural philosophy. The Ptolemaic system. By 1500s, natural philosophy has started to generate syntheses of the geometrical measurement of motion, as well as the known dynamics, meaning the cause and effect relation of motion. Copernicus realized that putting the sun at the center of the universe makes explaining the major anomaly rather most simply. Thus, simplicity became a major factor in considering the plausibility of his model. Take note, however, that Copernicus is actually wrong in putting the sun at the center of the universe rather than just the solar system. In his time, they yet don't know solar system, even terms like Milky Way galaxy. the universe basically consists of the same heavenly spheres that's supposed to revolve around a center. Anyway, in his book on the revolutions of the celestial spheres, he argued that the following simplified basic assumption of the universe. The sun, here indicated with a red spot, is at the center of the universe. The Earth, meanwhile, is just one of the other planets revolving around the sun. Shown here are the orbits of Mercury and Venus in the inner circle, and the orbits of Mars, Jupiter, and Saturn on the outer circle indicated here. These circles are, in fact, a cross-section of spherical shell containing those orbits of the planets. Moreover, that the orbits are basically circular. The universe is also spherical but deemed very large. In totality, the model proposed by Copernicus very closely resembles our model of today, except for two major points: that the sun is not the center of the universe, but only the center of mass of the solar system, and that the orbits of the planets are not circular, but only almost circular. In other words, Copernicus is almost right. This is understandable because he is still dependent on the scarce astronomical datasets and on the limited knowledge of the nature of matter and motion. The belief in the two domains view of the universe still prevails. Many specific Aristotelian conclusions on motion and matter prevents acceptance of the Copernican proposal. In the end, Copernicus had to propose his model as, at least, as much simpler alternative for computing planetary positions rather than a model of reality. Because of the lack of physical evidence, his model reverts back to mere mathematical saving of appearances. In fact, if we look closely, the system devised by Copernicus is mathematically equivalent to the scheme of Ptolemy. Here's an animation I lifted from Wikipedia. It shows an animation of the relative positions of three objects: the sun as a yellow dot, the earth as blue dot, and Mars as the red dot. On the left, the Copernican system offers a model in which the sun is at the center with the two planets revolving around it. On the right is the Ptolemaic system employing an epicycle motion of the planet Mars. For this, the earth remains stationary. Note that at any point in time, the relative formation of the three objects remain the same. Okay? To help you see the mathematical equivalence, here are the different obvious instances when the two systems produce equivalent relative positions of the heavenly objects. You can use the lines as guides and the order of colors. On the upper left, you see Sun, Earth, Mars alignment for both systems at the same instant of time. On the lower right, you will see the alignment of Mars, Sun, Earth for both systems and also at the same instant of time. The other two instances also show exact relative positions of the three, the lower left being triangular and the upper right being linear. Here is another go in the animation. The planets will align right now and then there. Okay. So, while the Copernican model is mathematically equivalent to the Ptolemaic model, the Copernican model still offers a few but major advantages over the latter. The model of Copernicus offered a better picture of the universe relative to what we now know so far. The best part is that it offers much simpler explanation of these known observations: retrograde motion of planets, changing phases of the inner planets, Venus and Mars, particularly Venus because it's the brighter of the two, variation in the brightness and apparent sizes of the planets over many months. As mentioned earlier, retrograde motion is one of the anomalies of motion of the heavenly bodies observed. Retrograde motion refers to the reversal of a planet's motion relative to the background stars as observed from the Earth. The Copernican model explains this apparent reversal as a short-lived parallax as the mid-ground, in this case planet Mars, moves along the direction of motion of Earth. As the Earth approaches along the slower orbit of Mars, the usual apparent motion is observed. However, as the Earth catches on, retrograde motion happens until such time that the Earth passes through and overtakes the planet. You can watch many videos on YouTube explaining retrograde motion according to the Copernican model. One such link is available in the description. Apparent brightness and size cannot be attributed solely from heliocentric models since relative positions are the same. However, if one uses a telescope, the phases of Venus becomes obvious and appears to follow the same sequence of phases as that of our moon, from relatively full Venus, like the full moon, to becoming gibbous or crescent, to new Venus, like the new moon, a very faint, and then back again. At this point, the Ptolemaic model does not allow planets to break the crystalline spheres, resulting to a limited motion of Venus and keeps it between the Sun and the Earth. Allowing the planets to pass through the crystalline spheres would require rational explanation unless we simply argue that the Ptolemaic system is just a tool for computation. Here, you will see that the Ptolemaic model actually predicts that Venus does not go through a gibbous phase. Meanwhile, the Copernican model perfectly models the phenomena, recovering the proper sequence of Venus phases. You can see here that it predicts a full to gibbous to quarter to crescent to new, and then back to the same sequence: crescent, quarter, gibbous, and full, and again. However, with the increasing accuracy of astronomical observation and the availability of data, the Copernican model largely fails in predicting astronomical formation and events. The Ptolemaic model still turns out predicting more accurately the other anomalies of the planets. Thus, Copernicus is forced to add epicycles and other mathematical devices to his original simpler model. This gave rise to a more complicated but comparatively accurate version 2 of his original. So we now have at least two Copernican model. Copernican model version 1 without the epicycles and other mathematical devices, and Copernican model version 2, which more complicated in a way, no? We can now somehow quantitatively evaluate the models using 3 of the 5 criteria according to Edward Wilson. These 5 criteria were discussed in Module 1 of Physics 10 online. 3 criteria is listed here: economy or simplicity of explanation for the same phenomena, mensuration or capability of the model to provide predictions or measures commensurate to the measured real-world observations. The third is consilience or consistency with other scientifically established laws or most recent system so far known to be correct. One can simply provide ranking of the models to make it simpler based on each of these criteria. And then later on, we'll get the overall ranking. We begin with economy. Obviously, the ranking from simplest to most complex is from the original version of Copernicus, for its second version, and the Ptolemaic model comes last. And so we put here the rank 1, 2, and 3, respectively. Come next, mensuration. In this case, we can say that the second version of the Copernican model comes close with a tie with the Ptolemaic system. In this case, we shall use 1.5 as ranking for both to keep the total of all ranks to 6. 3 plus 1.5 plus 1.5 is 6.
Consilience is what comes next. It would be a balanced judgment to place a ranking like this, rather than the second version and the Ptolemaic system a tie. This decision, as it will turn out, will also be a slightly paradoxical conclusion. So we say that the most consistent with the prevailing views about the universe is the Ptolemaic system. The Copernican model is, in a way, a very revolutionary one, as it reintroduced a rather old model of the Greeks. The version 2 of the same Copernican model can be said to be slightly consilient.
These evaluations result to a sum of ranked numbers as shown here in each column. The Copernican model version 2 is, in the best case scenario, just as best as the Ptolemaic model, with a score of 5.5, both of them, and the Copernican version 1 having 7. Now, if we analyze the situation using this ranking, what will a slightly simpler but generally mathematically equivalent model provide other than simplicity? All astronomers seems to be okay with adjusting once in a while the latest Ptolemaic system as more accurate data arrives. Given the slight inconsistencies of the Copernican model with the prevailing philosophies of nature, it is hardly a difficult one for any scientist to objectively and easily switch models. Besides, even Copernicus claims that his model does not necessarily give the picture of reality, rather than it's just for simpler computation only. In the end, it's actually a choice of which computational device you consider more accurate and are willing to use. The last straws for the Copernican model are largely based on timing. He lived during the great upheaval within the Catholic Church brought about by the allegations of the mistranslation of the Bible, the first book to be printed using the latest printing device invented in 1440s. This was the time when manual transcription done by the Catholic monks started to be replaced by the printing press, a much faster process of producing larger number of copies. This resulted to a rapid increase in vernacularization, a process of translating the Latin Bible into local languages such as the German and the English languages. It has been approved since the 9th century by the Church, this vernacularization. However, such vernacular translations must be done with care, as it often provides opportunities for losing the artistic or the poetic meaning unique to the original language, as well as the possible infusion of interpretations by the translators themselves into the translated texts. This probably helped fan the already heated debates between theologians related to biblical interpretations or exegesis. To make matters worse, internal problems in the church leadership ensued since the Western Schism, which started in 1378, resulting to the confusion in the authority of the office of Peter within the church. To make matters even worse, there arose bishops and church leaders who did not take their Christian faith seriously. They took advantage of the Pope's request for financial support in building sacred buildings in Rome, connecting donations for indulgences. Indulgence is a clear doctrine that can easily be misapplied and abused, and as has happened during the time of Martin Luther. The 95 Theses of Luther was meant to reveal these malpractices, especially those of indulgences. When mixed with political conditions of Europe at the time, things cannot get worse. And so we can say that the last straws for the Copernican model are two items: the scriptural and theological basis, and the other one is the physical basis. The scriptural problem arose with the background of Protestant Reformation and biblical exegesis apart from the church historical interpretations. Literal interpretations do not allow the earth to move. Others even claim that sun-centered universe leads to sun worship. The support of Giordano Bruno, a highly regarded Dominican prior and philosopher and cosmological theorist, you can search for his name, used the Copernican model to extend his theological interpretation of the Copernican cosmology. This led him to deny several essential and core Catholic beliefs. He is also known to believe in pantheism and transmigration of the souls, positions condemned by the Christian faith. The more significant last straw is rather the physical evidence, or the lack of it. The first expected physical evidence in favor of a moving Earth is the stellar parallax. However, because of the wrong estimate of the size of the universe, although already highly improved from the time of Ptolemy, stellar parallax are still unobserved until the middle of 1800s, some 300 years away. This second straw is largely caused by the well-established Aristotelian notion of motion. The Aristotelian physics relies on what he called natural motion. Natural motion is a concept whereby objects move without any effort from an external agent. Today, we know that the natural motion is rather moving in a straight line and constant speed. Based on the prevailing observations of their time, however, all objects naturally fall into Earth, as we also observe now. Thus, the projectile motion that includes horizontal motion is the one explained by Aristotle as violent motion. since such kind of motion is often accompanied by explosions or application of forces such as cannons or in bows and arrows. Observations also show that lighter objects fall more slowly, especially when demonstrated to fall within liquid water, or oil for that matter. When objects move within fluids, such as air, water, and oil, as I mentioned, the object is affected by what we call drag force, as shown in this illustration. As allowed to fall freely under the influence of gravity, this free fall is opposed by a viscous force called drag force. Hindi drugs nabawal na gamot. Since as speed gets higher, the drag force increases until it matches the weight, resulting to the approach of the speed, what we call the terminal speed. This terminal speed is known to be proportional to the mass, or its square root. The Aristotelian physics concluding that the rate of fall is therefore justified. The phrase rate of fall must be equivalent to the terminal speed of today. Thus, using the prevailing Aristotelian physics, most observations obviously contradict a moving Earth. You have already seen this in the early part of Module 2. The main problem, therefore, lies in the specific applications of the Aristotelian tradition for motion or movement of bodies or objects, both here on Earth, the terrestrial domain, and in the heavens, the celestial domain. Due to lack of support, both theologically and physically, the heliocentric model of Copernicus did not acquire traction to his contemporary astronomers. This results to a general rejection of his model in favor of the generally more accurate and more conciliant Ptolemaic system. Here are other references for the development of cosmological models that you may find interesting. These links are also placed in the description of this video. So we shall end this part and rest for a while before we proceed to discuss the appearance of new and better astronomical data, the new physics or new science by Galileo, and other events that led to the acceptance, at least in principle, of the Copernican model, though ultimately in a different form, the Keplerian model. Thank you. By the way, don't forget to take on the quiz that your faculty in charge will be sending you.